Welcome to the Office of Undergraduate Research Education series. Today's session is on the argument behind statistical analysis, and our speaker is Greg Stoddard. This is a virtual event and it's being recorded, so we ask everyone to mute yourself and turn off your camera to ensure the best experience. If you have questions, please use the chat feature or unmute yourself when you're invited by the speaker. This is the evaluation, the QR code. We would love everyone to complete this after the presentation, but we want to remind the SPUR and Europe scholars that you must complete this in order to receive credit for attending today. And the mission of the Office of Undergraduate Research is to facilitate and promote undergraduate, student, faculty, collaborative research, and creative works in all disciplines throughout the University of Utah campus. And we would like to acknowledge that this land, which is named for the Ute tribe, is the traditional and ancestral homeland of the Shoshone, Paiute, Goshute, and Ute tribes. The University of Utah recognizes and respects the enduring relationship that exists between many indigenous peoples and their traditional homelands. We respect the sovereign relationship between tribes, states, and the federal government, and we affirm the U's commitment to a partnership with Native nations and urban Indian communities through research, education, and community outreach activities. And now I'd like to introduce today's speaker. It's Greg Stoddard. He's the co-director of the Study Design and Biostatistics Center.
Thanks, Shelley. Thanks, everybody, for attending. I have a lot of slides, so let's hold the questions to the end. That way I can get all the way through them. Then we'll use whatever time's left over for questions. These are my topics. I'm going to describe what the discipline of statistics is. How do we do research, which I like to say, ask nature questions, what logical argument is being applied, and then I'll explain what Statlab is, which is expert statistician consulting available to each of you. That doesn't cost you anything. So starting with a simple question, what year of college do students enroll in college algebra? To answer the question, we'll collect some data. We'll obtain the year of college from the 30 students in one section of Math 105 college algebra in the current semester at the University of Utah. Like every research question, we quickly discover the answer is not a single number, like 1, which would be the first year. Instead, we have a collection of 30 numbers that vary. You could list them out to 30 numbers. To better understand the data, we summarize it using a frequency table or with a histogram to visualize the data as a distribution. So you can see the 5 possible choices, the number of times they occur, which sum up to the sample size of 30. And then we take each of these, divide by sample size to get the percent of those responses. And this is the running sum of the percents. So look over here at the picture. See that goes up to 33, it goes up to 27, and so on. So there's your answer. What year of college do they enroll in algebra? You can see it's a whole distribution. There's not a single number. And that's true of nature. Everything's a distribution. Now let's take a slightly harder question. We want to see the relationship between 2 variables. Specifically, how much does birth weight increase for births between 26 and 40 weeks gestation? A possible approach to take is introduced in middle school around 7th or 8th grade. Recall we have these ordered pairs of x, y, or x, and then the Cartesian coordinate system, and then we plot this over here, -2, -3, and then we draw a line through them, which has this equation, y equals a, the y-intercept, plus b, the slope, times x, which is that. Unfortunately, a graph like this, where all the dots line up perfectly on a straight line, is a deterministic function. There is no such function in nature. In nature, the graph looks a bit more fishy. It looks like this. You got your straight line, but it doesn't go through the dots unless we extend with these vertical lines here. Statistics provides a solution. We fit a line where the vertical distances, which are these little fish bones here, are minimized, so the line is simultaneously as close as possible to each of the XY ordered pairs. Here's what the birth weight looks like. Where I did blue for boys, pink for girls. There's the equation of the line. So you can see the slope. For every 1 week increase, you increase your weight by 1.93 grams, which is about a half pound. All right, but notice that I have a distribution at each point on my x-axis, taking this end one here, the 40 weeks, show it. So in this graph, even after holding sex and gestation constant, because I'm doing it simply for the boys here, we see that we ask the question, why is it that not all the babies have the same birth weight? The reason is because distributions occur in nature as the result of multiple causality. A whole lot more goes into determining what your birth weight is going to be than simply gestation age or even gestation age plus sex. So we think of this as the sufficient component cause theory. In this little pie diagram, each pie is a sufficient cause where all these components, which are the pie pieces, are in place. And once the last piece is added, causation occurs, and whatever that you're modeling occurs, like I guess your birth weight. And then we have multiple causes because there's more than one way for something to occur. You could think of a auto accident. Any one of us could come up with a dozen scenarios. One of the scenarios might include drunk driving, one might include you fall asleep, icy roads, and all the other moving vehicle, and so on and so on. So when you say something causes something, it's not true. There's not a single thing that causes it. It's one component of multiple other things that have to be in place before that one thing can actually cause the event. Let's go to a more difficult question, which is the most common research problem, and that's where we compare two groups. So we conduct a study where chronic low back pain patients are randomly assigned to receive either an active drug or placebo and then treated for 3 months. Using the data, we in the FDA need to decide if the drug worked. Here's what the data look like, where I'm drawing a smooth line through the top of the histogram. Got my placebo group black, active drug blue. And you can see this line of discrimination here, but basically one group's right on top of the other one. So how do you decide if the drug worked or not? It looks like most of the time placebo is going to work as good as the drug. So this is what the data look like. How will the FDA decide to approve the drug for chronic low back pain? That decision requires a logical argument of a statistical analysis, which is the point of the lecture. All right, so we're going to derive it from scratch. We'll begin with a simple coin toss. We guess it'll come up heads. Flip it, it did. We guess again it's going to come up heads. This time it comes up tails. We toss it 100 times, it comes up heads 50 times. Then we realize we cannot predict with certainty how a single coin toss will come out. However, since it comes up heads half of the time, on average, we can be confident that we have half a chance it's going to come up heads. So back to our drug study, how likely is the drug going to work in an individual patient? With a little thought, we should realize that we cannot predict with 100% accuracy what will be observed with any individual observation from any distribution, including how well that drug's going to work for an individual patient. However, if we turn our attention away from individual observations, an extremely important phenomenon appears. In spite of that irregular behavior of individual results, the average of many results shows a striking regularity. In statistics, we call that property statistical regularity, and we also even derived a theorem from it. We call it the strong law of large numbers, which is the very basis statistical theory. In fact, it's all we really have. So here I have X bar the sample mean, where you just sum up each of the individual observations by the sample size, and it says that it goes to what the mean is in nature or in our population we sampled from. It gets closer and closer as our sample size gets bigger and bigger. Okay, we can demonstrate that using simulation. I'm going to sample from a random number generator that mimics the normal distribution, which is that bell-shaped distribution. That look like my drug data. Take samples of size 1 up to 500 for each study group, compute the means from each sample and plot it. So the simulation for when there is a difference, here I'm going to have a mean of 50 for placebo, mean of 55 for my active drug, standard deviation of 10, where standard deviation is basically the average distance an observation is from the group mean. So it measures the scatter. And this is what happens. You can see for small sample sizes, it's jumping around like crazy. I'm graphing the means here. But as my sample size gets bigger and bigger, it starts to converge on the true value. So we can think of that as signal to noise ratio, where the signal are the means and the mean difference, and the variability, which is the noise, is how individual observations jump around from each other, or the unpredictability of them. So it appears from this graph, we can be confident that the drug improves quality of life on average, as long as our sample size is at least 125. That's where we're starting to see this clear signal. However, we can't draw our conclusion from that because that was just a simulation where I intentionally designed it to show a difference. Let's see what happens if I do the simulation where there is no difference between them. I'm going to do it for the two groups, subtract the two means, and plot the difference for each sample. And it looks like this. You can see for small sample sizes, it's jumping around like crazy. And then it starts to converge on a true value of 0 of no difference as my sample size gets bigger. But notice from sample to sample, it will probably never be exactly 0. And since my simulation, I was sampling from a population where they were exactly the same, this is nothing more than a chance pattern in the data. It just got lucky and it came out that way, that it was different from 0. Right? That brings us to the empirical research conundrum. Let's say we collect some data, and here I'm graphing the mean. Each little circle is a data point in this C panel. Our data look like there is a difference between treatment and control groups. We like to say it's representative of what happens in our sample population, which is nature, which is panel A. However, it could be that it's just a chance pattern of data, and that in nature, there's actually no association. Okay, you can see that these dots here could have come from the top part of that graph, and the dots there could have come at the bottom part of that graph because they're lined up. So we don't know what happened. And that's our problem. We observe something, but we don't know, is it just a chance pattern? On the second sample, maybe it'll look very different. And every sample, it always does look different. So we need a logical argument to settle the conundrum. This argument includes a statistical hypothesis test, also called a significance test. Our task now is to derive a way to perform such testing. All right, since all we have in statistics is this statistical regularity, we have to base it on that. So I'm going to invent the statistic I'm going to call T, which is the two-sample t-test. I'll do the signal in the numerator, noise in the bottom. So it's a signal to noise ratio. The signal is this mean difference, which here I'm denoting as the mean sample mean for group 1, sample size mean group 2, and subtract them. And then in the bottom, the noise is the variability of the mean difference, which this is just how much jumping around is going on with this mean difference up here, or at least on the one where I actually graphed it as a mean difference. And these are called the standard errors. This is standard deviation, which is the average distance each observation is from its mean divided by the square sample size. And we have to add them in the denominator because both groups contribute variability. So when I take a sum or a difference, it actually increases. All right, so that little formula right there captures that graph. And you can see as my sample size gets bigger, I'm dividing by a bigger number here, which makes the denominator smaller. And if you divide by a smaller number, it makes the numerator divided by the smaller number makes the t-statistic bigger. So that t-statistic will get bigger and bigger as my sample size increases, which means it becomes more and more a correct ratio as I allow for more and more statistical regularity to settle in. Okay, now we have a way to quantify it, and we use our data to compute it. what we need next is the way to determine if that quantity, that t-statistic, is simply due to chance. To do that, we need to bring in the concept of probability. A probability is simply a proportion, is the portion of events making up an outcome divided by the number of events possible, like 5 heads divided by 10 coin flips. Right? Here's, for example, let's say the probability dies, a roll of a single die will come up a 3 on come up 3. The probability we roll a 3 is one event, possible event out of 6 die face possibilities. So 1/6. This is called a simple probability. A conditional probability first conditions on something has already happened and then computes that proportion. For example, the probability the die comes up 3 when we already know it came up an odd number is like this. Probability we roll 3, this vertical line is read as, given that it came up odd, is one value out of 3 possible odd numbers. Now let's roll 2 dice. Here's the face of the first die, here's the face of the second die, and I sum them. I have 36 possibilities, and these are the sums. So probably it comes up 7 is 6 times, as I count up these numbers of 7s here, divided by number of possibilities. So it's 1/6. And then I can graph that as a histogram. There's the 1/6, here's the 6/6, which is the 7s, and so on. And now I can compute the probability by the area of the curve, where the curve is simply this upper outline of my histogram. So the probability I get a 3 or less, which is it came up a 2 or a 3, or given it came up 11 or greater, so 11 or 12 here, which is probability 11 or 12, I just sum all those up and I end up with 1/6. So it's the area of the curve there plus the area of the curve there. Well, we're going to use that in a moment. So coming back to here, our conundrum, we have to solve this problem, but it could have been observed, what could be our observed association, which just means mean difference, is merely a chance pattern in the data. So I need to come up with that probability. So I want the probability came up due to chance, but it turns out that there's no way to compute such a probability. We call it an untrackable problem. So to save the day, we use a simple workaround, which is a conditional probability, which can be computed. So the probability result was due to chance is essentially equal to the probability we observed a result at least as large as we did, given that no difference exists in the population, which is the same thing as the means are equal in the population. So we have to come up with a way to do that probability. We're simply going to use the same thing we did with the sum of the 2 dice trip. We'll construct a distribution of all the possible values that t-statistic can take on when there is no difference between the means and the population that we're sampling from. Then we simply use the area of the curve to the right of t, added the area of the curve to the minus t, and that's our probability. We call that a 2-sided p-value. We're allowing for one group to be smaller than the other one, as well as adding for one group to be larger than the other one. So difference in either direction. All right. It turns out that curve is a well-known function called the t-distribution, which looks like the normal curve for those of you who've seen a normal curve before. Just a little slightly thicker tails is what the t-distribution is compared to the normal curve. All right, so here's my t. I observe 1.98, and the area to the right of that is 2.5%, and then I do the minus of that, 2.5% on that side. So my p-value then is p equals 0.05. Then when p is small and p is less than or equal to 0.05 is a popular criterion, we say that we have achieved statistical significance and conclude that result was not likely due to chance. We do that because it was just too improbable, so it must be due to something else. Hopefully, we'd like it to be that there really is a difference in the population. All right, so it seemed like I just dreamed something up. It's actually theoretical statisticians derive it all with formulas in mathematics. If you do a simulation, turns out you get exactly the same number, because the whole theory of statistics is based on that statistical regularity, which is the long run average. So we ask ourselves now, that statistical hypothesis testing, is it simply an arbitrary practice, or is it actually based on logic? It turns out it is based on logic. It follows the logic of proof by contradiction that's used in mathematics, as well as anything else, any other discipline, by the way. So here's how it works. We take a P and Q to be two propositions, which is simply a statement that it's either it's true or it's false, and we take on two values. And we start by the opposite of what we want to disprove. So we'll suppose not P. And then we'll do some operation, and that'll lead to something, proposition Q. We do some more operations, it leads to the opposite, not Q. But since it can't be Q and not Q at the same time, we say it's a contradiction. And since all these operations were valid, the only way that can occur is if our beginning proposition or premise was false all along. So that allows us to conclude the opposite, because we know that's false. All right, let me show you an example. I'm going to prove that division by zero is undefined because it's meaningless. So we'll start out with the opposite. Suppose division by zero is meaningful. Then we arbitrarily choose a number different from zero. And then we divide by it to get another number, which we can do because we're going to assume our opening premise, where we can divide by zero, is a valid operation. And then I'm going to multiply both sides of that by zero. So I've multiplied that side by zero, the zeros cancels, I'm left with A. I multiply that side by zero, and that turns into zero, because we know that when you multiply by zero, it becomes zero. And now I have a contradiction, because I have both A not equal to zero, and I have A equal to zero. Well, they both can't be true. So we conclude the opposite of our opening premise and say division by zero is meaningless. All right, now we're going to apply it to hypothesis testing. So proof by contradiction is the logical construct of hypothesis testing. We assume there's no difference, that in the populations the means are the same. We compute the test statistic from the data, which is obviously a valid operation. And then we compute the p-value from that t-distribution that assumes that there is no difference. So now we're applying that opening premise. And then we observe p is close to zero. Let's say, like my example that I just showed you, p is 0.05 or less. So we observe a small p, but it should be close to 1. Because if there is no difference, I would expect these two means to be basically the same number. So the numerator of my test statistic is 0. So when I divide by whatever is in the denominator, it's still going to be close to 0. At least my t statistic will be 0. And then I do the area of the curve from the middle of that distribution. The area to the right is 1/2. The area to the left is 1/2. So I sum them together for my 2-tailed p-value. And I should get a number close to 1. So now I have a contradiction. I observed a p close to 0, but it should have been close to 1. But it can't be both. So it's a contradiction. The only way that could have happened is my opening premise must be false. So I take the not of that, which is the opposite, and say that the two means are not equal. So in an introductory stat class or an introductory stat book, they say this is the null hypothesis, which we refute and accept the alternative hypothesis, which is the opposite. Well, it's actually taken out of context. If that's all you do is you do a test statistic, get a p-value, and draw a conclusion, which is what people do when they only had a single stat class, they always get the wrong answer because there's actually competing explanations. You simply can't go from there to there. And what I'm about to show you is because the two competing explanations is that your study was biased or it was confounded. All right, but we'll come back to that in a moment. Now I want to point out that although the logic follows a proof by contradiction, it is actually not a proof. So the more correct way to think about it is to call it a demonstration by improbableness. It's not a proof for two reasons. If we use the criteria that p less than 0.05 to eliminate chance, there's still a 5% probability that the result was just chance. So nothing is strictly proven. There's still a 5% probability that there is no difference in the population and that it just was a chance pattern. And then the second reason, there are two competing explanations for the mean difference, like bias and confounding. So instead of concluding this alternative hypothesis, we have to state it like this. Either the means are different in the population, or our study was biased, or our study was confounded. Let me quickly give you an example of what bias is. Let's say we're doing a study where we go look at children and we want to know if childhood smoking decreases your lung capacity, which it will measure using forced expiratory volume. We do our study, and sure enough, we do our study, but all the heavy smokers, childhood smokers, refuse to participate. And they're the ones that have the strongest signal. They refuse to participate because childhood smokers, by definition, are rebellious. So they rebel and don't want to be in your study. So we have a biased sample, which doesn't represent what we need it to represent. So you call that selection bias. An example of confounding is we think we've observed a correct association, but it's really due to another variable. So if we did that study in children from, say, 4th grade up to high school seniors, we'll just quickly discover that smoking actually improves your lung capacity. The reason it improves it is because the smokers tend to be the high school students, and they have larger lungs, and larger lungs allow you to expel more air when you do the breath testing. So we think it was due to cigarette smoking is helping you expel more air, but in fact, it was simply due to unequal lung sizes. You simply had a bigger lung. So to control for that, but you eliminate study design bias by careful study design, make sure you get a good sample. And confounding, you can control for that and make everyone have the same lungs size. And a statistical regression model allows you to do that to control for confounding. Your study is still going to be confounded, however, because if you didn't collect data on parental smoking, it could be where smokers tend to have parents who also smoke. Just think about it. If you have a young, healthy lung, a few puffs on cigarettes not going to make much difference. But if you're hanging around your parents who are smoking nonstop in the house and in the car, you're going to be exposed to a lot of secondhand smoke. So even after I control for confounding in our sample, and we finally can show that smoking decreases your lung capacity, it might not have been the childhood smoking at all. It could have been the parental exposure. That's really hard to get that right. And if you don't even think about bias and confounding, you simply do a significance test. That's why I say you always get the wrong answer, because it's so easy for bias and confounding to slip into your study if you don't carefully avoid it. All right, so to make hypothesis testing work, we have to add on an additional logical construct. It's called the disjunctive syllogism. You simply list all, you observe an effect, you list all the possible ways that that effect could occur, which are these bias, confounding, chance, or there really is causation. We call it association because we can't prove it's causation. You want to say it's association that caused the effect, you first have to eliminate those three things. So if you simply eliminate chance and those two are left over, you didn't apply a sufficiently rigorous logic to your experiment. So how do we apply this disjunctive syllogism? It's the IMRAD structure of that you use when you publish in a professional journal, where you have, it's an acronym for introduction section, methods section, results section, and discussion. So in this guideline here, they say that isn't just an arbitrary format. It's the direct reflection of the process of a scientific discovery, which is a sort of a simple way of saying you apply the disjunctive syllogism. So the way you do that is you don't just jump in and say that you observe an effect. The reader's not ready to believe it. First, you have to convince them that you eliminate bias. So in the method section, you say all the things you did to eliminate bias, how you carefully selected your sample to avoid selection bias, for example. And then you explain how you control for confounding by explaining the regression model that you're using. And then the results section, that's where all these p-values are going to be. That's where you eliminate chance. And you might eliminate a little bit of confounding if you use a regression model. And then finally, after you convince the reader that it's not due to any of those three things, finally in the discussion section, you can make this claim that the association is real. All right, so between the proof by contradiction, which is really a demonstration by improbableness as one logical structure, and the disjunctive syllogism, where we eliminate bias and confounding as well as the second logical structure, you can see that when you do a scientific study and you do it well, you actually have a logical argument to claim that your result's true. It's hard to do, though. In fact, you should just assume that half of every published article in a scientific journal reached the false conclusion. Some even claim it's even closer to 100% of them are wrong, because it's so simple for bias and confounding to slip in, and researchers aren't good at avoiding it. So for all of you now who hopefully want to be researchers, there's some help. Statisticians are very good at thinking about all those things. What's the correct statistical method to use? What are potential sources of bias and confounding, and how to deal with them. So if you have a statistician in the closet that you can pull out when you need them to help you with your study, that would be ideal. And we're offering that. So I'm the co-director of the Study Design Biostatistics Center, which is housed up in the medical school. We consult for all the faculty all over campus. For students, however, we don't really offer that service because students can't pay for it like faculty who have grants can. So we're introducing this thing we're calling Statlab, which is an opportunity for our PhD and biostatistics students to get more consulting experience. And at some point, we'll expand it to include second-year Master of Statistics students. But they're not really good at it, but they're better than someone who is not a statistician. So I'm going to supervise them. I'll meet with, as they meet with you, I'll also be in the meeting to make sure that they don't give you bad advice. So to contact us then, as long as you're doing serious research, where you have a faculty member that you're gonna co-author with, he's gonna collaborate with you. And you intend to publish in a professional journal, as opposed to you're just taking a stat class and you want someone to tutor you. We only do these serious research problems. Otherwise, we'll be too overwhelmed. Just send me an email, and I'll hook you up with the Statlab. And then I also teach a bunch of stat courses. Notice they're all graduate level classes. When I was an undergraduate, I knew I wanted to be a statistician, so I ran around campus and took every single stat class that University of Utah offered. And most of them were graduate courses, and I was just an undergraduate. I did fine in them, and you would too. So even in my classes, this one here, the last one, is where I teach the Master of Statistics students how to actually do real world research. Even that one, which is the most sophisticated of all of them, you would do fine in. So if you might need a permission code, but you can contact me if someone's giving you a hassle and I can help you get it. So if you want to take any of these classes, where I actually, it's not really teaching you mathematics, I'm simply saying how to analyze data in the real world. You're welcome to enroll in any of those. All right, so that's it. Does anyone have questions?
Well, Greg, a question from a registrant. They asked, what is p-hacking and how can you tell if a researcher is doing it?
That's a really great question. P-hacking is where you have a whole bunch of variables you collected. So there's a whole lot of possibilities for doing a significance test. You have a primary question and then you test for it, and you found out you didn't find any significant difference. So you say, wait a minute, that means I can't publish because no one's going to be interested in my publication. So you start snooping around your data and come up until you actually find something that's significant. When you do that, you increase your probability you're going to find a chance pattern, even though you're applying a statistical test to it. So what happens if when you publish that, someone else comes along and tries to replicate their work, you can't, because it's not true in the population. It was just, you just got lucky and it came out that way in your own particular data set. So if you do that, you're supposed to say in your discussion section, warn the reader that that was just an exploratory finding, which needs to be confirmed in another study. Most people don't make that statement. They just make you, and they actually reword the study to sound like that was your original hypothesis all along. For you to spot if that's happening is almost impossible. If someone's proposing a hypothesis though that seems a little far-fetched, and you don't really believe that would have been the original question, I guess that's the only way to know that was just a p-hacking conclusion. That's all I have to say on that.
Okay, another question. What's the best scenarios to use stats rather than other types of evidence?
I actually don't see a way to not do it. Because when you ask a question in nature, there's a distribution. Nature is just a collection of distributions. And the only way that you can make sense of it is to apply mathematics to the distributions. And that's what the field of statistics is. It's how you add and subtract distributions and draw conclusions from the data. I guess you could think of that you simply do qualitative research and ask for someone to describe their lived experience. That's actually really good, is a really great way to do research, but there's not really hypothesis testing to take that information and apply a hypothesis to test. Was it just a chance pattern that the people you were talking to would say that, and in future people, they wouldn't say the same thing? You're still back to statistics. So statistics is always needed from my point of view.
Okay, another question is how can we help people with a lack of faith in science understand why we can trust statistics?
The answer is you can't. Um, we there's a someone named Iona Dantus. I don't remember exactly how to say his name. Revived made a big deal about this about 10 years ago, that probably everything that you read in in journals, professional journals, are false. Um, and when he did that, the media took hold of it and sensationalized it, and that's what killed the credibility in science. Um, but he was right. People are not good at um, doing good research where they eliminate bias and confounding. They simply apply statistics. And if they don't get the answer they want, they keep snooping until they find something that is there, but with p hacking, and then no one can reproduce it. So um, you're never going to be able to convince them that it's good, but it's certainly better than doing nothing. Occasionally we get it right. We do the best we can with what we have. So we actually progress knowledge by doing research and applying statistics. So it's better than simply just observing things and then drawing conclusions from that. So believing something happens because you keep seeing it, that's not good evidence either. So eventually you're going to see it where it doesn't, the opposite occurs.
Okay, I guess one last question. What was your drive behind entering this field? And do you still have passion for it? If so, what would that be?
I can't think of anything I would rather do. I never heard of statistics. Um, to, Nowadays, they're teaching it in high schools, which is really good. Um, but I've never heard of it. I was actually got my first job at the university as a secretary for a professor at the College of Nursing who was doing research, and he showed me the statistical software he was using. He let me run statistics for him. And I thought, wow, and I discovered I had a knack for it. And so this is really, really fun, and I'm good at this. Um, so that's how I was introduced to it. And then, so I've been a statistician my whole life. The reason it's so fun is because, um, in some sense, you're creating knowledge rather than just reading about it that someone else said. So that's what's exciting. It's really exciting to get your name published in a scientific journal as well. So I've got about 300 publications now, still going.
300, that's impressive, Greg. Well, do we have any other questions? There's a question in the chat. Do you think journals should be incentivized replication studies and the publication of negative results?
Oh, absolutely. For the longest time, journals didn't really like to publish a negative result where you didn't find anything because they didn't think the readers would be fascinated by it. So there was this publication bias, which is only positive findings were being published. And we're trying to get journals to stop doing that uh, because some people do studies, they find it, some people do studies and they don't find it. And then the readers are wondering, is the effect real or is it not? So they do things called meta-analyses where they find all the published papers and try to come up with the average finding that everyone has and draw conclusions from that. But if most of the papers are only the published findings, it's still going to give you the wrong answer because you're going to say there's an effect there because you had more studies that said it was there than didn't say it was there. So the only way that we're going to actually converge on truth is if journals accept the role that they have to publish negative findings as well. What was the second part of that question?
I think you covered it.
Okay.
Yeah. Do you want to if there are no more questions, we can go to the last 2 slides. Well, thank you, Greg, for this great presentation. Here's the QR code for the event evaluation. I just put the link in the chat. A reminder that SPUR and Europe scholars must complete the evaluation in order to receive credit for attending today. And I just want to remind everybody that the Office of Undergraduate Research, we're in the SIL Center. Our website is our.utah.edu, and you can email us at our@utah.edu. And thank you again, Greg. We really appreciate it.
Thank you all for listening to me.